Okay, here's where we're going to explain that weird stuff about the two twins. You know, one of them flying off to another star, coming back and being way younger than their identical twin. It's pretty strange. And in an earlier video, I think it was the AP number 7 one, we did introduce Einstein's theory of special relativity, did a little bit with it. We had these two very innocent assumptions up here. We'll discuss these in more in a second. And it led to this weird stuff when we really looked at it. We got these things like time dilation and length contraction and the increase in mass as things get faster or closer to the speed of light. Um, Now, it might have seemed at that time that we'd explained the twin paradox. You know, how one twin could end up like so young. Like what happened to the time? Well, time dilation. That doesn't get it though, because do you remember? It was symmetrical. Each of those mad scientists thought the other one was aging too slowly. So that really doesn't get it. I'm not saying there's these two twins trying to like out compliment each other. My goodness, you've just hardly changed. No, no, no. I mean, I'm really old. You're the one who's hardly changed. They get in an argument, Southern style kind of thing. No, no. I'm saying one of them really is younger. Wherein lieth the asymmetry? Where did this difference come from? I'm going to explain that in this video, maybe more things. We'll see how it goes. But I wanted to leave these innocent assumptions up here. Another quick look at them. This one right here, motion is relative. You can't say who's moving. Did I pass you or did you pass me? Now on the Earth, it might seem like you could tell. I mean, because there's a landscape and all these surroundings. But even there on a moving Earth, right? See, like moving Earth. But out in the middle of space, you pass by each other. Who's to say who's moving? Fair's fair. It's so egalitarian. It sounds like it ought to be in the Constitution or the Declaration of Independence or something. You can't say who's moving. I'm moving, you're moving. Okay. Anyway, the second one, the speed of light's the same for everybody. Another wonderful egalitarian kind of thing to say. Everybody deserves the same speed of light. All speed of light, people are created equal with regard to what they measure for the speed of light. But relative to what? Because, you can't say who's moving. That's where it gets weird. And the weirdness of that, is it true? Well, we talked about that in the other video. There's real good evidence to think this is true on its face. But if that's not enough for you, consequences come from this. And the consequences can be independently validated, verified. And yeah, you know what? I really believe this stuff. I might be wrong, but hey, people a lot smarter than me believe it. So in any case, we're going to see where the consequences go. Now, I have to introduce something here, a space-time diagram. That sounds all fancy, highfalutin kind of stuff, but really, here's all I mean, is we can draw a graph where we have a time on this axis and position on this axis. I'll call it X. And that's a little bit too low down. But anyway, let's see. So I'm going to put a nice little grid on here. I'm going to put, good. That's, golly dang it. I think I have one with a grid on it, but I don't know where I put it. We'll just have to go with it. Anyway, so here is a graph of when and where things happen. We can number them. This is a really not a difficult concept that we're about to see here. Like this is where you are on some number line, across the floor or out in space or wherever you want to put these little numbers. This is what time it is. 1 o'clock, 2 o'clock, 3 o'clock, 4 o'clock, 5 o'clock, whatever. And so this is something that happened at a place called 2 at a time called 1. Yeah, okay. So it's just it's a record of where and when things happen. A little space-time diagram. Now on this diagram, I want to show a light beam. To show a light beam, I think I want to pick for units. I think I'm going to pick years for the time. Nice long stretched out time. And I'm going to pick, what down here? Light years. A light year is a distance. It is not an amount of time. A light year is how far light goes in a year. And it's really far because light's really fast and a year is kind of a long time. In fact, since light goes about 300 million meters a second, 300,000 kilometers a second, around the world 7 times in 1 second. Since it goes that fast, then in a year, it goes almost like 6 trillion miles. So each of these is 6 trillion miles. Now, I want to show a light beam. I'll make a nice red light beam. It's some red laser, I don't know. And light goes the speed of light. That means it goes 1 light year every year. So a light beam would make, and I wish I had a pencil to, oh God, that's gross. Can you just pretend that's straight? Usually I draw better. Anyway, that's supposed to be a light beam going the speed of light. Now, I want to draw, since I'm talking about 2 different twins, let's say this is the earthbound twin. Do we need names? Eartha. There was an Eartha kit, right? Anyway, Eartha and Spacey. Those are terrible names. Anyway, but you'll remember which is which. So Eartha stays home. Her sister Spacey takes off in a rocket. I'm not going to make her go 99.99999% the speed of light because I can't draw a line that close to that and let you tell them apart. So what I'm going to do is use blue here and make her just go 6/10 the speed of light, or 3/5 the speed of light. 3/5 the speed of light means she would go, let's see, 3 light years in 5 years. So this is a picture of Spacey's rocket. Oh, she's a rocket. And she's moving off, kind of chasing the light beam, but not keeping up with it. You see, after like 1 year, she's only 6/10 of a light year from the Earth, whereas the light beam is a whole light year from the Earth in a year. So she's not keeping up with it. Thing is, think about what a t-axis means. If I look at this line here, it's different times, but they're all in the same place. It's all in a place called 0. This is all in a place called 1. So basically your t-axis is home. Home is where the heart is. Home is where the t-axis is. So this right here is Spacey's home away from home. It's the spaceship. It is her home, so she calls it x equals 0. It's her own t-axis. And as seen by Eartha, Spacey's moving. Yeah, I guess so. Here's the thing. Spacey needs an x-axis. Common sense, which is going to get shot to pieces here, but common sense would tell you that they would agree on their x-axis because the x-axis is the set of all things that happen at the same time, a set of simultaneous events that happen at the beginning. You know, like start your watches, and everybody can be synchronized, you know. It is a common sense assumption that they should share x-axes. However, we have a problem. See this thing about the speed of light being the same for everybody? You see how this red line of this light beam going the speed of light symmetrically split right down the middle these 2 Earth axes and made like a 45-degree line just as far from each one. That's a light year per year when that line splits right down the middle of those 2 axes. If I choose this as Spacey's axis, then she's moving almost the speed of light, or though the light beam doesn't look like it's going very fast, like she's almost keeping up with it. And common sense would tell you that, but common sense is going to be a problem. The trouble is here, this right here, this assumption that the speed of light is the same for everybody is going to force us to do something really weird. It's going to force us to draw a different x-axis for Spacey. In fact, Spacey's x-axis is going to have to be symmetrical with respect to what I've done. I'm not doing a great job here with my, that's not so bad. That's her x prime axis. That is the set of all things that Spacey thinks happen at the same time. Now, events happening at the same time is like this. You know, like here's something that happened at home the day that Spacey took off, and Earth and Spacey both agree on that. Here's something that happened you know, at the same time, way out 5 light years away, but according to Spacey, when she's moving, it happened before the other one. You're heading towards something that happened before that. I'm on track to explain the twin paradox about how you can end up younger than your identical twin, vastly younger than your identical twin. But on the way, there's a really neat paradox I read about in a book by Roger Penrose. It's called The Emperor's New Mind. And Roger Penrose is basically Stephen Hawking's mentor, so smart guy. I saw him talk one time at Georgia Tech. It's really, really neat. Talked about some crazy stuff I could hardly understand. But anyway, Roger Penrose wrote this book, and I remember this example he gave in it. So I'm kind of borrowing it. I'm going to take liberties with it. It's like the Andromeda paradox. You could look it up. But anyway, in my slightly different version, there are 3 psychics in a park. And one psychic is walking east at 2 miles per hour. Another psychic is walking west at 2 miles per hour. And the third psychic is sitting on the park bench. And they're all talking to each other, you know, without opening their mouths because they're psychics. Okay, the psychic walking, I'll say the psychic sitting on the park bench, psychically says, as the Andromeda galaxy, 2 million light years away, rises on the eastern horizon, the psychic on the park bench says, oh my gosh, I'm getting a reading. The Andromedan Space Council is about to vote right now on whether or not to attack Earth in an irrevocable action. You know, once they launch the spaceships, they're not coming back, and Earth is going to be invaded. Might take them a while to get here, but it's happening right now. The psychic walking toward the west, because she has a different x-axis. Now, walking I was just 2 miles an hour walking. That doesn't amount to much. I mean, this is the speed of light. But the thing is, if you extend it, even if this axis is only barely tilted, you extend it out 2 million light years. It's like a couple of weeks. So the psychic walking towards the west says, oh, no problem. They're not going to vote for another 2 weeks. They're still holding debates. We can psychically influence them. Penrose didn't do this part. Anyway, we can psychically influence them and stop them. And the psychic walking toward the east has yet another, let's say, actually, that's the psychic walking to the west probably had this one. Psychic walking toward the east says, too late, they're on their way. Now, I'm talking about 3 different presents, 3 different sets of nows for 3 different people, depending on how they're walking. That doesn't sound like a common experience, but you don't generally talk about what's happening in the Andromeda galaxy right now. Kind of hard to tell. What's the resolution of the paradox? Maybe there are not any psychics. Maybe that's it. Maybe there are no psychics. Or if there are psychics, maybe they can't telepathically communicate faster than the speed of light. And if that were the case, then all this would be old news just arriving from 2 million light years away from 2 million years ago, and the Andromedans would either almost be here or didn't come. And I don't know if you totally got that one, but I'm just illustrating how weird the relativity of simultaneity can be. It messes with now. Now that I've said that, it is what it is, and I'm going to stick with it. And we've satisfied this postulate right here in trying to build Spacey's axes, her graph. But there's one more job we have to do. This is maybe the hardest to follow part of it. I'm going to be very careful. I'll try to make it as clear as I can. I've sort of had a little practice doing this. I don't know if anybody understood. Well, we'll try again, right? The thing is, look at this. Motion is relative. This means that they can't disagree on any statement they make about the other one. Like if one of them says, you're talking too slow, the other one better say, no, you're talking too slow. It has to be symmetrical. Let me show you. Best way to do this is very brief, trial and error. I'm going to set up some tick marks and show you that they don't work. And then I'm going to fix it and you'll see what I fixed. What I'm going to do first is say, what the heck? I'm just going to put tick marks like this. I mean, why not? And when I say tick marks, I mean I got to put my 1, 2, 3, and so forth years and light years on there. Now, if I do this, what I can do is, Spacey left on their mutual 20th birthday, and now it's their 21st birthday. And so they went to celebrate each other's birthday. Now, according to the way I've done the tick marks, this shows that in Eartha's world, Spacey is having her birthday exactly at the right time. 1 year after launch. The trouble is, if I'm going to draw weird slaunch-wise axes like there, they got to have slaunch-wise, my dad used to say that, slaunch-wise lines. In other words, I'd have to have, these lines that went like that. It looks like an accordion. It'd be sort of like that. You can see what I'm doing there? And these are the lines along which you'd have to read numbers off. So the thing is, whereas Eartha sees Spacey have her birthday at the right time of the year, we have to look at where this dashed line, I know this is hard to see. I'm going to follow along here. This is the birthday party back on Earth, and it to Spacey appears to happen sometime between 1 and 2 years, at about 1.6 years. No, it can't be that I think you had your birthday at the same time as my birthday, but you think I had my birthday way later than your birthday. They don't match up. I'm going to fix it. I almost think I should draw a bigger. I'll fix it as best I can. Hope you can see this. What I'm going to do, I'm going to do a one-time fix on these tick marks and show you that it works. I'm not going to try like 3 or 4 times and narrow in on it. I'm going to get it right this second time. Let's see. It's right about here, and here, and here, and here. Do you see how these things are stretched out? Let me show you why this works. According to this, Spacey's 21st birthday is seen to happen at about 1.25 years. So that in Eartha's world, Spacey was 1.25 years too late having her birthday. Now, I'm not saying she watched her birthday. I'm going to get to that in just a minute. But that she should be having it, at that time, 1.25 years later. All I'm asking for is fairness, symmetry. So let's see if we get it. Let's follow one of these slaunch-wise lines along where I got to draw my little thing parallel to this one. And here I go. Here's the first birthday party back on Earth. And it meets up. I'm paralleling that, it meets up right here. Nailed it. 1.25 years. It may be weird, but it's fair and just. Each of them thinks the other one had a birthday 3 months too late. Time dilation. I just actually showed time dilation on this graph, and by the right amount. The factor gamma that I talked about in the other video, that's 1 over the square root of 1 minus the speed of light fraction, I'll call it beta squared. It turns out if you plug in 0.6, which is the speed I chose for the spaceship, you get 1.25 and it works. Okay, so I got it. Now I'm about to throw the twist in there, the asymmetry. I just argued our way into having weird collapsed up axes because I got to have the speed of light be the same for everybody. And I played around with the spacing of the tick marks in order to establish fairness and justice, that motion's relative and you can't see who's moving. Having done that, what I want to do is get out to right here and turn her around and send her home. Spacey decides ain't nothing to see out here. She's coming right back home. So if I just flip this thing around and have her come home at the same speed, here she is. She comes home. This stretched out spacing that has been forced on me to obey the postulates now results in this being 3 years and this being 4 years. And oh my gosh, this is weird. What we've just shown, couldn't find any way around it, it was forced on us, is that while Eartha lived 5 years, Spacey lived 4 years. Now, this isn't as extreme as the 4 days and 80 years thing, because I didn't want to pick a number as close to the speed of light as that. This is more modest, but it's still dramatic. I'm telling you that Spacey will have only witnessed 4 years. She'll have only biologically aged 4 years. Her atomic clocks and little wind-up clocks, everything else would have all said 4 years. She would only need 4 years of food or supplies. Really, it's been 4 years for Spacey and 5 for Eartha. Really. So how could this even look? How do you even, what if they zoomed the whole time? I would have said, watch a video or watch a FaceTime. I could have said FaceTime. Nowadays, doing all this Zoom stuff. Hope it's secure. I don't know. Might not be. It's not. But anyway, they zoom the whole time, secure or not. And while zooming, they watch each other. And the way they look, there's a little complication here I'm going to show. The thing is, they can only watch each other with light signals. That's what radio waves are, is light. And they travel the speed of light. So let's see what happens if after 1 year, Spacey sends a light signal back to Earth to simply say, happy birthday, it's my birthday, must be your birthday, I'll say happy birthday. So she tries to zoom, sends a signal back to Earth. It's got to be a 45-degree line, because remember how we made the speed of light 45 degrees on here? So it's this 45-degree line, and look where it shows up. It shows up at exactly 2 years. This means that it takes 2 years for Eartha to receive a birthday message that was sent after supposedly 1 year. If they don't just do the birthday thing, if they keep zoom on all the time, then Eartha will see Spacey living, aging, doing everything too slowly by a factor of 2. You know, like taking a sip of water, like that. What about the other way around? What does it look like when Eartha sends Spacey a signal? Well, she sends one after 1 year. And if you look closely, I'm going to parallel the speed of light thing. Beautiful. I'm liking this. Spacey receives Eartha's first, anniversary birthday thing after 2 years also. We have symmetry. Each one thinks the other one's aging too slow, just like we wanted. Now, by the way, this effect we're seeing is not too different from, it's superficially at least similar to what's called the Doppler effect. You know, when you hear like a car go by, like, they hear your pitch drop, or the ice cream truck, like that. I even heard a jackhammer one time. They were using a jackhammer on Virginia Avenue over there, and it was so weird. I heard both the pitch and the frequency of the concrete slabs change. Let me see if I can try it. It's like like that. Not as dramatic, but it was noticeable. It was weird. Anyway, this is sort of the Doppler effect. Sometimes it's called the relativistic Doppler effect, where you're moving away from somebody and they look like they're all doing everything too slow and low frequency. But it's not quite the same as the sound, because there's no medium for the transmission of the waves. Okay, each one sees the other one age too slowly, so how does the age get different? It happens right here. That's where it happens. The very instant that Spacey turns around to head back to Earth, instead of having these light waves play catch up with her and hit her infrequently, she takes her jet ski in the ocean starts driving right into the waves. Slap, 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 because she's coming at him, right? You're going to hit him real frequently that way. And I'll show you that happen. You see, look at this second birthday message. Whoa, it appeared after 2.5 years. And what about the third birthday message? Now we're back kind of even again. What about the fourth birthday message? It happened at 3.5 years. And the fifth one happened after 4 years. In other words, what Spacey sees is she sees her sister age too slowly for 2 years by a factor of 2. 2 Yeah, so that she only ages 1 year and 2 years. Weird. She's real young back home. But then sees her age 4 years in the 2 years she comes home, and 1 + 4 is 5, and she sees in 4 years, sees her sister age 5 years. What about what Eartha sees? What about the messages that Spacey sends home? I'll show you those messages. Here was one of them. And again, it looked like she's aging too slow. Same thing here with this message sent after 2 years, arrives after 4 years. So Eartha spends 4 years watching Spacey age too slowly by a factor of 2. Finally, she sees her age too fast. This birthday comes in fast, and well, oops, we're out of time. You know, not for the video, but for this. If you see someone age too slowly by a factor of 2 for 4 years and too fast for 1 year, it ain't time to catch up. You didn't see him get very old. Let me shift into the view when I get the numbers back to that extreme example with 99.99999% the speed of light, where gamma's a lot, you know, big, 70,000 or something, whatever it was. So now it looks like this. Eartha watches Spacey go out there, and Spacey's just aging glacially slow, just like hardly doing anything, barely moving, like taking all day to put a spoonful of cereal in her mouth. She sees that happen for decades, for like 79.99 whatever years she sees that happen. Finally, she sees Spacey starting to come home and suddenly go into incredible overdrive, like, you know, like super fast for like a few minutes. And she sees her age an amazing like 4 days in a few minutes, and then she's home. And she's only watched her age like 4 days. But look what Spacey sees. Spacey sees Eartha also take forever to put some cereal in her mouth for like a couple days, and then sees her go into overdrive for a whole 2 days. And when you watch your sister live in an overdrive for 2 whole days, you see your sister age 80 years, and they're back together. I don't know if you quite followed that or not, but that's how it is, and that's what really happens. These kind of things can be tested. I'm actually going to connect this with something else before I maybe go into some other point. Notice the turnaround. See, you go like this and you turn around. That is one intense turnaround, really slamming on the brakes and firing the engines the other direction, really, really hard. In the words of her therapist, and how did that make you feel? Made her feel heavy, made her feel intense. You know, the G forces of turning around, you know, like how many G's was that? So for a short time here, she experienced what was like a tremendous gravity-like effect. Now, Einstein has this thing in general relativity called the equivalence principle, where if it feels like gravity, it is gravity, and if it feels like acceleration, it is, and gravity and acceleration are the same thing. One doesn't cause the other, they're the same thing. So actually, this is like gravity. And this is why, like in the movie Interstellar, you might have seen the scene, if you saw the movie Interstellar, you might have seen the scene where they go down to check out this planet with big waves, kind of shallow water and big waves, and they're down there for an hour and a half. And meanwhile, up there, their buddy ages like 23 years or something. It's because there was this gargantua black hole they were near, and it was, you'd have to ask Kip Thorne for the technical specs on that because he was their technical guy, relativity guy. But in any case, this is like gravity. Gravity does this. So like I'm actually aging more slowly, standing right where I'm standing, than I would be in my daughter's old bedroom right above my head. Oh, by the teeniest, tiniest little amount. Deeper in the Earth's gravitational field, and I'm a little heavier feeling. So it's like doing this acceleration turnaround thinking I'm aging slower, I really am. The effects would get extreme, like with a black hole, where gravity gets so strong that you'd age super slowly because it'd be like intense. So that's weird. Twin paradox. Let me throw in another one. There's another story I can tell called the pole and barn paradox. In this one, you've got, let's say, some kid is practicing for the track team, and it's his senior year, and maybe there's no coronavirus that year, so he gets to actually have a track season. Anyway, he's practicing on the farm because he was on the farm, and with this 20-foot long pole. His dad is his coach, awkward sometimes, tells him to like run around real fast because he's practicing with the pole vault. He's going to run. And he runs 87% the speed of light, which gives you a gamma of 2. So length contraction that we discussed in the other video for the dad sees the pole shortened by a factor of 2. So the pole is not 20 feet long, like the kid thinks it is, like it was bought. It's only 10 feet long. And Dad has his son run through the barn. The barn is 15 feet long and has like sliding garage door things on it, automatic work or remote or whatever. Barn's 15 feet long. The kid with the relativistically shortened pole vault pole is told to run through the barn. Kid's in the barn, and Dad pulls a fast one on him, thinks it's funny. It's a little practical joke. He hits the barn door closers that simultaneously close the barn doors, so that the kid with a 10-foot long pole is completely trapped in a 15-foot long barn. Dad thinks that's pretty funny, but he doesn't want his kid to like crash into the barn door at 87% the speed of light, because that would probably release a couple hundred megatons of energy and lay waste to half the state they live in. But anyway, so he opens the doors back up. The kid runs on out, spends about a year decelerating, misses graduation, whatever, slows down, breathlessly comes up to Dad and says, "Hey, how was that? That was pretty good, huh?" Dad says, "Yeah, it was. How'd you like when I had you like stuck in the barn?" Kid said, "What do you mean?" "Well, I had you in the barn. I mean, your pole was 10 feet long, and the barn was 15 feet. So you were in the barn, had the doors closed, and you were in there, and I'll let you out. I didn't want you to like pull up to stay." The kid says, "No, Paul, that's not what I saw." "Well, what'd you see?" "My pole was 20 feet long the whole time. You stupid barn over there was only 7.5 feet long." See, it was length contracted for him. "No way I fit in that barn. My pole was sticking out both ends." "Did you see those barn doors shut?" "Yeah, I did." What'd the kid see? He couldn't have seen the barn doors shut with him inside the barn because his pole's way longer than the barn. So what'd he see? Let's see. I could make you figure it out. And if you really want to think about it, you can pause the video, think about it, because I'm going to tell you in about 3 seconds. 1, 2, 3. Okay, now thinking. You got it, right? The relativity of simultaneity. Two events that happen at the same time for one observer don't necessarily happen at the same time for another observer. What happened? What did the kid see? Think about it. The kid's coming along. The kid, just like the Andromeda psychic heading towards the Andromeda galaxy, thinks they already voted and already launched. Kid sees the far barn door come down first and close. Well, that's weird. The near barn door is still open. The pole gets into the barn, and when the pole is partway in the barn, the far barn door opens up, letting that end of the pole out. Back end of the pole still sticking out the back of the barn. Slightly later, the back end gets into the barn, and like some weird afterthought, the back barn door closes, like what for, and opens back up. So that instead of it being chop, chop like that, trapping the kid in the barn, it goes like, letting them through. It's almost sneaky like that. And all these relativistic paradoxes, weirdnesses, involve this kind of thing where, You think you got them. You think you got it trapped, and it's got something up its sleeve. Well, that's enough for now about these two paradoxes. I might make yet another video with some of other weird things in it. There's a lot of weird effects. This will do for now, though, and remember that next time you go upstairs, life's going to fly by just a teeny weeny bit faster. Or when you go to the store and back, you'd have spent more time staying home. Okay, enough of that. We'll talk more.